point here. So if you haven't already, please go ahead and put your Penn State email into the chat box for me. That'd be awesome. And we're going to talk about so the second half of lessons that we've been talking about this semester. So lessons 6 through 9 for our second midterm here. So, and obviously ask me any questions at any point that you have, but at the end we will have some review questions and obviously an open Q&A if you guys have any more things that you want to ask. So the first thing we talked about was correlation in general. So we just kind of talked about how what correlation is. It doesn't have a value to it. It's really just talking about the strength and direction of something. So the strength is going to be represented by how large the number is, and then also our direction is going to be represented by if it's either like plus or minus. That's going to tell us the direction. So basically all that a correlation is showing you is kind of like how closely together is our data. Are they representing each other? Is that something that we can use later on to kind of show that there's a relationship here? And we do use that, we represent it by the letter R, so correlation also with the letter R here. And then just some common rules. If our correlation is 0, that means that it indicates no relationship, while if it is 1 or -1, we do have a perfect linear relationship. And the main difference there would be if it's 1, it's going to be a perfect positive linear relationship, and if it's -1, it'll be a perfect negative linear relationship. Okay, and then we talked about an equation of a line. So basically this is when we're trying to discuss what basically what equation makes the line that we draw on our graph. So if we were to draw this out, and for example our line looked like this, if we were to go through this, so A is our y-intercept, so that would be right here. That would be wherever our line intersects the y-axis there. And then we have B, which is our slope. So that's basically our rise over our run. So whatever this like incline here is going to be our slope. And then lastly, we do have what our x value is just going to be whatever we choose at that point, because this is our x-axis down here. So any of these points can be x, and then that's how we're able to find the equation of the line. So this entire line would be the y equals a plus bx. So remember, our b is going to be our slope, a is our y-intercept there. So the slope is just basically telling you how much of a change is happening as you increase your x, how much change is happening, vertically. All right, and then so when we're talking about correlation or regression, it is important to realize that we can have issues with these. We can't use the data that we have to make assumptions about data that's outside of what we already collected. So something called extrapolation that we talked about is basically saying that if you use your regression equation to predict things that are not something that you took data on, that would be extrapolation. So saying that you think that you can predict what's going to happen in the year 3000 when you only have data from the years like 2005 to 2010. You can't extrapolate, and you can't assume that that trend is going to stay the same past that. So the main thing that comes from that is that correlation does not equal causation. If two things are correlated to each other, that does not mean that one causes the other. So that's just an important thing to keep in mind. You don't want to make assumptions that are not necessarily going to be true all the time there in that case. So things can be correlated and they can show that there's some sort of relationship in there, but we can't say that one causes the other. So that's the main idea there. And then also the idea of illogically interpreting your y-intercept. So remember, our y-intercept is going to be the value where our x-axis and our y-axis, like where it intersects between our line and the y-axis. So that'll technically be when x is equal to 0. So if we were to draw that out, it would look like this. So our y-intercept is going to be right here. And so technically this is going to be when x equals 0, which is going to be on this line right here. And then the idea of illogically interpreting your y-intercept, this is, let's say we were talking about like the amount of time in something. So let's say the amount of time that you spend I don't know, brushing your teeth in the morning, and let's say the data that you got was anywhere from like 1.5 minutes to like 5 minutes or something. So when you find that, you want to make sure that if you didn't find data or anything that was like for 0 minutes, that's not going to be something you can interpret. You can't, decide that, oh, for 0 minutes there's going to be a relationship with this y variable here. You can't do that because it doesn't make sense, you know. So if it doesn't make sense for your x value to be 0, then that means that it since it doesn't make sense for that, that means that you're going to have to recognize that we can't use the y-intercept to say something like causal about the variable itself. You know, it may exist, you know, x equals 0, may have an intercept there on the y-axis, but that does not mean that it's able to be interpreted. And so that would mean that it'd be like, so, and this would be talking about if we were in like, talking about like time, and then let's say our y variable, we could say like hours slept or something. So we're trying to find out if there's like a correlation between the number of hours that you sleep and then the number of minutes that you brush your teeth. So I'll just put this here. And I just made this up, so. But so basically here, that would be saying that they didn't brush their teeth at all, 0%, or 0 minutes. And then that would go, and then whatever this, you know, y variable is, let's say that this is technically, you know, y variable of like 5, but let's say that the people that you found data about were only, you know, from here to here, so you only found data from people who, you know, they brushed their teeth from either 1.5 minutes to 5 minutes max. So that means that, you know, basically your first y variable starts right here. So we can't extrapolate and bring it down here if we didn't have information about the data down here. So we don't have information about people who brush their teeth for 0 minutes, who don't brush their teeth, you know, so you can't make that assumption that people who, you know, brush their teeth for 0 minutes, you know, sleep 5 hours or something. It's basically saying like we don't have enough data to conclude that. Also, if there's something like, if your y-intercept turns negative, so let's say you have a graph like this, and I wanted to look at, you know, the amount of, let's just say like the growth of like someone's like plant in a month or whatever. So we'll just say like this is the growth in centimeters, and then this will be like the amount of time in the sun or something. So in this case, we want to make sure that we don't want to misinterpret this y-intercept. So technically, you know, this y-intercept down here is at x equals 0, but it's going to be a negative y, as you see, because it's on the negative, one of the negative parts of the graph. So we can't say that it grew a negative amount. You know, if we were talking about, you know, how much it like decreased, that might be something that we could get into. But in this case, if you see that the line is linear and it's positive, we won't be able to interpret this this value down here as being something that, you know, relates to the growth in centimeters and then the amount of sun. Because that would basically be saying that, you know, it would have, basically it wouldn't have grown any if they had like this negative amount in sun. So you can't have like a negative amount of sun. That's why you couldn't interpret this y-intercept to mean that down here, because it is in the negative part. Does that make sense? Okay, cool. Good question, though. It's definitely a concept to, you know, practice and read over a little bit if it's a little confusing. Okay, so we talked about risk and odds, which are basically talking about the likelihood of an event happening, although we do interpret them in different ways, just given the denominator of the equations we use to find them. So risk is basically our same thing as like the probability of anything, because it's just saying the probability that something's going to happen. So, and you hear stuff like the risk factors, so that's saying, you know, your risk of, you know, getting a disease or your risk of this and that. That's just saying the probability that it will occur, you know, period. That's it. So that's why our denominator is talking about our total number of outcomes, because we're trying to find out, you know, the probability that it's going to occur in general. So we have our number with the outcome divided by the total number. For odds, we want to compare it to it happening versus not happening. In order to do that, we just have to change our denominator here to, you know, we keep our numerator as the number with the outcome, but then for our denominator, it's going to be the number without the outcome as our odds down here for our denominator. And another way you can write that too is our, it's if you already have like the risk value, you can just say risk divided by 1 minus risk. So remember, risk is talking about the probability that an event will occur. So that, you know, makes sense that the probability of an event not occurring would be 1 minus risk. So the probability of it not occurring. So, and that's just like a probability rule there. And that's why we're using that as our denominator, because 1 minus risk is also the same thing as this denominator up here for a number without the outcome. So the, you know, the risk that it would not happen. So that's risk and odds, just some common equations that we use there to describe different variables. And then also, when we talked about relative risk, well, I mean, when we talked about risk in general, we did have two different types. We had our relative risk and then our increased risk. So increased, most people understand, just it is what it sounds like. It's, you know, how much higher the event happening is it than, you know, it not happening. So our increased, the risk of an event happening is this many times higher for group 1 than group 2. So we use increased risk when we have things to compare, because obviously if you're talking about something increasing, you have to have something to compare it to in the beginning. So if you're trying to talk about, you know, the risk of getting a certain disease from males to females, you know, you're going to be comparing it from group 1 to group 2 and then how many times higher it is. So that's what our increased risk is. And then relative risk, to go back there, is our risk of one group versus the risk of the other group. We just divide those. So basically, this is more so talking about not how much higher, but it's just saying how much more likely group 1 is to experience it than group 2. So it's not telling you like how much more likely it is, but it's just telling you like the amount of times more likely. It may not be an increase or a decrease, but that's why relative risk, that's why it's relative. You know, we don't know if it's increased or decreased or whatever. It's just saying how much more likely they are to get it. So, and then your increased risk is that relative risk that we just found, -1, because that's going to give you the rest of the risk there. So that's going to tell you the amount of it, or the risk of it happening, and how many times higher it is. Okay, and then Simpson's paradox is just a concept that we talked about. Is basically just talking about the observed association between variables. And then, you know, it's similar to when we talked about like confounding variables, that there could be a variable that can change or even reverse the direction of another variable. So the example I often see is that if you're looking at two variables, like someone's race and then their opinion on the death penalty, you know, in court, and, you know, you're finding it, maybe there's a correlation between someone's race and then if they think that, you know, someone should receive the death penalty or something. And then, but then the issue there is that there could be a third variable. So we're not taking into account the victim's race, who would be receiving the death penalty, or, you know, the victim of the person receiving the death penalty. So because that third variable of the victim's race, you know, can play a part there, that can totally change the entire association that you find between those variables. Basically saying that, you know, race and opinion are not the only two variables coming into play, dependent on the person's decision on if they think the person should get the death penalty or not. So main idea here is that, you know, if you don't know the whole story, if you're not taking information and demographics from every single variable in your study, then you might have something happen like this. So it's kind of going to give you an invalid idea of what like you're actually trying to look at, and it's going to kind of give you a skewed idea of what the actual association is that you're trying to find. Okay, so probability is something we talked about quite a bit, and there are 5 probability rules that we use these are like our basic rules that are always true. So our first one is that probabilities have to be between 0 and 1. That's just a common knowledge. And it's important to think about, you know, if we are taking you know, you do an equation and you're trying to find a probability and you get a number, if it's not between 0 and 1, you know, you did something wrong there. You know, probabilities do have to be positive. And then, you know, they also can't exceed 1, so they have to be a decimal there. Or they can be 1 or 0. 0 means there's no chance, 1 means there's a 100% chance. Our second one is that, so if you add the individual probabilities together, if they can't happen simultaneously, then you find the probability that at least one of them occurs. And we'll do some examples with this, but basically it's saying if you have a bunch of different probabilities that can't happen at the same time, so, you know, the probability that it, you know, rains in State College, snows in State College, and there's a hurricane in State College. Honestly, maybe this could happen at the same time, but theoretically, if you think about weather events, they can't all happen at the same time. So if you would be able to add those together in order to find the probability that at least one of those things were to occur, because since they can't happen simultaneously, they're not related to one another, and that's where that happens. And then our third one's going to be that 1 minus the chance of the opposite thing is the chance of something. So it kind of sounds a little confusing. This is one that, you know, it's better to see examples with and get practice with to understand. So it's basically saying that if you're trying to find the probability of something, and you know the probability that it wouldn't happen, all you have to do is take the probability of 1 minus whatever the other thing is, and then you're going to get the one that it would happen. And the main idea of this is just the fact that, you know, you always have two parts to your probability, you know, so this is like your probability of it happening, and then this is going to be the probability of it not happening, and then this is going to give you like your total probability, okay? So in this case, you know, if you were trying to find the probability of it happening, you could just do like probability of, or sorry, 1 minus the probability of it not happening. That's going to equal the probability of it happening. It's really just algebra, you know what I mean? It's because, you know, you always have, there's, you know, two sides to every probability here, and then you want to make sure that you're trying to find the opposite. All you have to do is 1 minus the one that you have currently, and that'll be able to give you the value of the other one. And then the fourth one, so if you have independent events, once again, you know, they don't affect each other, then you can just multiply them, their chances together, and then you're able to find the probability of those independent events happening. So this one uses multiplication, this one uses subtraction, this one uses adding. And then this last rule is kind of just conceptual in the fact that if you, so I'll just read, if the ways in which one event can happen are a subset of the ways that a second event can happen, then the first event cannot have a higher probability. So this is just saying that if the ways that something can happen are, you know, coming after, you know, different chances of the first thing happening, then the first event can't have a higher probability, because in that case, if it did, then that would kind of mess up the sub-steps. So the main idea of this is that there's the sub-steps can be, you know, confusing if you would change the probability. So if you stick by this rule that our first event can't have a higher probability if the event that happens is a subset of the ways that the second one happens, then you're able to go forth and make that conclusion. So that's the main thing. You just want to make sure that you're looking at how they interact with each other, you know, because probabilities can interact with each other. You know, we were talking about if they can't happen simultaneously or if they're independent, that kind of thing. But in this one, we're saying, you know, if you have a probability that is dependent upon another event happening, then this fifth rule does come into play there. So that's the main idea of that one. Okay, so yeah, a few things also about probability just to talk about. So if we have mutually exclusive events, that just means that they can't happen, that they have like no outcomes in common at all. So if you had an event diagram, there wouldn't be any center coverage in there. And then since they have nothing in common, and like we talked about in the probability rules, if they can't happen simultaneously, then the probability that at least one of them occurs, all you have to do is add them together. So remember, if things can't happen simultaneously, then you can just go ahead and add them together in order to find that probability that at least one of them occurs. And then again, if we're talking about independent events, so ones that don't affect each other, then that means that we can just multiply the chances. This is kind of just, you know, expanding a bit on the probability rules. So yeah, so then the chance of one thing doesn't change when you know how the others turned out, and probability of both occurs found by multiplying those chances together. And then the last one we have is just that the probabilities of an event can be simulated by repeating the process many times on a computer. So this is basically saying, you know, because we don't, when we're taking samples, you know, it's hard to take samples over and over and over again, take a bunch of samples. And okay, I'm holding on. Are you good now? Okay. Okay, so yeah, basically the probabilities that an event can be simulated by repeating the process. This has to do, you know, when we would use stat key and, you know, keep pressing, you know, like to make a bunch of samples. That's just saying that since we basically aren't able to do that in real life often, that we can simulate it accurately by using something like stat key in that case. Okay, so then our expected value is basically talking about that if we were to do a process, like take a sample over and over and over again, or whatever the different process we're doing, that what we expect to be the average of the values that we get is going to be our expected value. And the way that you find that is just your sum of values times the probabilities, and that's going to give you your as like the total amount. So like your sum of your values and then multiply by the probability of each. So if you have like a 20% chance of rolling a 6, you do 0.2 times 6, and then a 30% chance of rolling a 3, 0.3 times 3. So that's just basically saying that given all of those, the chances of all these different things happening, if we were to multiply them all and add them all together, that's what we would expect to get over time. Okay, and then our law of large numbers, basically all that is talking about averages or proportions, and then how stable we think they would be when we have more trials. And then also, so it's basically the main idea is that the average or proportions are going to be more stable if you have more trials. However, then the sums or the counts are going to be more variable in that case with those large trials. So that's the main idea of law of large numbers. And then this disclaimer at the bottom is just saying that basically you're not getting these stable proportions because we had like a bad run of luck. Because since if you're doing all these proportions, then, or if you're doing all these different trials, they're independent of each other. So like this it has no memory, so the one doesn't affect the other. So that's the main idea of that there. Okay, and then sampling distribution of summary statistic. This is literally just saying if you were to take all your statistics that you found and then put them onto a distribution, such as like a normal curve, dot plot, whatever, that's really all it is. And then that's where you're able to see that shape, and that gives you kind of more of an idea of what the variables are doing, what the data looks like, in terms of one another. Okay, normal approximation. So this is just a very, this is a main thing of statistics that we talk about, basically in the way that, if we have large random samples, they're going to be representative of the true population as long as, the samples are large enough. Because we want them, in order to represent the population, we want them to be as close enough to the size of the population as possible. That's why we want to have a large sample size. And then if they're random, that means that we can kind of take away from having bias or anything. So if they're random, they can just go on and on. And you'll make sure that you're able to have more representative of the true population in your actual sample that you got. So yeah, and then our sampling distribution of averages or proportions from a large number of independent trials. It's basically saying that it's going to be approximately normal if your sample is representative of that true population. So that's just a quote there that is like a definition of normal approximation, but it's basically saying that if we take samples over and over again and they're going to approximately follow the normal curve, and then we are able to make inferences about our sample statistics and then how they relate, how accurate are they to our population parameters. So that's the main idea there. And then these are just equations here to find your standard deviation of a sample mean and a sample proportion. So these are just different equations that you should know in order to calculate these when you're given the different values. So as you can see, we're using population, standard deviation, whatnot in order to find out what it would be for the mean, because we're inferring that they're going to be similar. And then same thing with the proportion. We're using population proportion as our basis for our sample proportion if we don't have that. All right, let's do some review questions. So if you haven't done this before, basically I'll go ahead and read through the question, and then we will, you guys can go ahead and try to answer it. If you don't know, just type in the chat box that you don't know, and we'll go over it. So yeah, let's try this one. So one airline has a better on-time arrival rate than a second airline in each of the 5 cities in which they compete. So true or false, is it still possible that the second airline has a better on-time arrival rate if you look at this data for the 5 cities combined? So try this one out and type your answer into the chat box, and we will go over it. Okay, good job, guys. Absolutely. So our answer here is going to be true, because basically if this were to happen, that means that it would be an example of Simpson's paradox. So remember, so suppose like on an airline, like if most of them fly out of the airport with bad weather, and then most of the other airline flies out with good weather, that can basically change our entire result. So that's why this is possible, if you looked at the data like that, because dependent on the weather, that's like our third variable that we want to make sure we're looking at for the weather in each different city. So our answer is true there. So good job, guys. All right, our second one, we have true or false. If there is a linear pattern to the data, then linear regression can be appropriately used for extrapolation. So let me know what you think about this one, and we will go over it. Okay, yeah, good job, guys. So our answer here is going to be false, because remember, when we have, like, extrapolation is really never good per se, because it's basically saying, like, we don't have enough data, so we're going to try to make assumptions about our data based on what we have. So just because the pattern is linear for like the range of the data that we observed doesn't mean that that linear pattern still exists. So you want to make sure that you realize that even though we see something in the data that we have, it doesn't mean that we can go ahead and make conclusions about data outside of that, because that doesn't mean that that same trend is going to hold true there. So our answer would be false. All right, let's try another one. So true or false, the probability that a randomly chosen household has at least one child under age 5 is 35%. So true or false, this means that the probability of a randomly chosen household has no children under age 5 is 65%. So go ahead and try this one out. Okay, yeah, this one's a tough one for sure. So this has to go back to one of our probability rules. So remember, kind of, it applies more so, that's a good thought. This applies more so to the idea that if you're trying to find the probability of something, all you do is take 1 minus the probability of the opposite thing. So we have the probability here that at least one child under age 5, that's 35%, okay? So if we're trying to find the probability of, I'll just put probability of child under 5, and then this is going to be 0.35. And we're looking for the probability of no children under age 5. So basically to find this, all we have to do is 1 minus the probability of the opposite thing, which would be the probability that the child is under 5, so that'd be 0.35, and then we would end up getting 0.65, which is 65%. So this would be true because that holds true for one of our probability rules. Does that make sense how I got to that? Awesome. All right. Let's do a few more. All right, so true or false, since the nature of the population does not matter, the sampling distribution of a sample proportion will approximately follow the normal distribution, even for a convenience sample. So try this one out and let me know what you think. Okay, so for this one, the beginning of it, it does kind of tricky. It does sound true, because our sampling distribution should be approximately normal if, our population is normal, first of all, but then, also if, we take enough samples, it'll eventually become normal. But this last part here, even for a convenience sample, this isn't true because since a convenience sample has no sort of randomization in it or any sort of like experimental value to it, there's no way for us to know. When we're taking those sampling distributions, when we're taking all the different samples, those are randomized. We're doing that with some sort of like idea of what we're doing behind it. So with a convenience sample, we're unable to tell, what that distribution would even look like anyway. So this is going to be false because there's no way that we can tell there with that convenience sample. Does that make sense? Awesome. All right. All right, let's try another one. So true or false, a normal approximation for the distribution of a sample proportion will work better when the true population proportion is closer to 1. So let me know what you think about this one, and then we will go over it. Okay, yeah, so for this one, remember, proportions are talking about, a certain number divided by the total number. So if something is completely, 50-50, that means that, our true proportion is going to be 0.5. That's literally saying that, you have a 50% chance on both sides, so that's what if it was close to 0.5, this would be true. This is what we want. But since it says 1, that's not true. So this is going to be false. Because if the true population proportion is closer to 1, that means that the distribution is going to be skewed to the right there, or excuse me, to the left, because they're going to have a lot of values over here closer to 1. That's where, the spread's going to be out here more because there won't be as many small values there. So when it's closer to 0.5, that's when you're going to get more of a normal distribution here. So that's why this would be false, because we want our population proportion to be closer to 1 there. All right, so a spinner can land in 8 possible positions so that all 8 have the same probability of coming up. Each position must have the probability of what? So read through these answers and let me know what you think. Alrighty, so yeah, our answer here would be D, so good job. So remember, if we're talking about probability, and since all 8 of them have the same probability, that means that together they all have to add up to equal 8. Or I'm sorry, 1. And then since there's 8 of them, you want to do that 1 divided by 8 in order to get, what each one would be. So technically, it would be like 1/8 plus 1/8, and so on and so forth. And you do this 8 times to get 1, so that means that 1/8 would have to be the position, or the probability for each of them, each position. So our answer is D. All right, good job. All right, one last one here. So if the points on a scatter plot tightly fit around the regression line, y equals 2 minus 3x, we can conclude that the correlation is what? So try this one out and let me know what you think. All right, so yeah, good job. Our answer is A here. So remember, if we're looking, sorry, I didn't mean to get if we're looking at our slope, so our answer is A. Our slope, remember, is going to be, if we remember our equation, y equals a plus bx. Our slope is this b here. So in this case, our b is going to be -3. So if b is equal to -3, that means that we have a negative slope here. So then, since our slope is negative, our correlation basically, accounts for the same thing. So it's asking, our correlation is going to be what? Well, our slope is negative, so that means also that our correlation would be negative there. So this would look something like this. If we had 2 here, we would have it looking something like this. The 2 minus 3x, so then our slope here would be over 1x and then down 3, so -3. All right, good job, guys. So that's all we got for tonight. So obviously you can watch back this review as well as the other reviews for the rest of the chapters if you want like more in-depth reviews for each of the topics that we just went over. If you haven't given me your Penn State email, please go ahead and type that into the chat box. And if you have any other questions, let me know and we can definitely go over that. If not, you guys are good for tonight and good luck on your midterm.